All right, good morning, everyone. We are going to start Unit 6 today, and Unit 6 is all about more application of differentiation. So last unit, we kind of looked at how do we use the derivatives graphically, and this unit is more going to be application problems and how we use that in regards to those. If you've taken physics, you've probably seen this, maybe presented in a little bit different way, but for the most part, we've actually kind of hinted at this a couple times throughout the examples that we've done in previous units, so hopefully you'll find this unit applicable when we do these. The first thing I want to talk about is particle motion. And when you're dealing with particle motion, you really have three different categories, I suppose, of motion. The first is just your left-right movement or wherever you're going in terms of your direction. That's your position function. Your second would be your velocity function. And then your third would be acceleration. And so a lot of times these are called PVA problems because that stands for position, velocity, acceleration. And mathematically, position, velocity, and acceleration work in terms of their derivatives, in terms of starting at the top and working your way down. So when you're dealing with a position function, that's like your original function. Your velocity function is how fast something is going. So in this case, in this problem, they're giving you in terms of meters and in seconds. So your velocity is your rate of change in terms of meter per second, which you can think of as rate of change if you want to. And that's your velocity, which is actually the derivative of position. So you can think about this as P prime if you want to. Your acceleration is actually the rate of change of your rate of change. And so that's in terms of its units, meters per second squared. I know it seems kind of weird to say this as rate of change of the rate of change, but that really is what it is when you're looking at this mathematically. And then you can think about that as P double prime or your second derivative of your position function. And so if you always remember position, velocity, acceleration, that kind of gives you the order in which you're finding the derivatives of each one. Okay, with that being said, I'm going to start with this first example. It says a particle moves along a horizontal line so that its position at any time t greater than or equal to 0 is given by this function where s is measured in meters and t is in seconds. Find the velocity at time t and at t equals 1 second. So again, you're finding velocity based on your position. So we need to go from here to here, which is finding the first derivative. So your velocity function is just taking the first derivative of this guy right here. And we can take the derivative of that pretty easily. That becomes 6t squared minus 14t plus 4. So this right here is the velocity at time t. That's part one. I'm going to highlight that then. That's what they wanted first. And then they want the velocity at time t equals 1 second. So really you're finding the velocity when your time is 1 second or v of 1, which we know to just plug, we know to just plug 1 in then for every t that we see. And when you do that, you should get -4. We're dealing with meters in seconds, so this is meters per second. And the -4 is really just involving what direction you're going. So at 1 second, your velocity is -4, which means you're actually going left rather than right, which we're going to get into here in the next example, but that is really what we're doing with this first part. Part B says, when is the particle at rest? Moving left, moving right, and we need to justify this one. So the particle is at rest mathematically when you're looking at your velocity of time equaling 0. So if your velocity is 0, that means your particle is at rest. You're moving left when your velocity is negative or less than 0. And you're moving right when your velocity is positive or greater than 0. So those are the three things we're going to look at. So in this problem, if we're trying to figure out when our particle is at rest, we have to figure out when does our velocity equal 0. And we have our velocity function from right here. We have to set that equal to 0 then to figure out when our particle is at rest. So I'm going to take 6t squared minus 14t plus 4 and set it equal to 0. In this case, I can actually factor out something here. Each term has a common value of a 2 at least. So I'm going to try to factor that out just to make that a little bit easier. That becomes then 3t squared minus 7t plus 2 equals 0. I just factored out a 2 from that previous equation. And then I can actually factor this. So what times what gives you 3t squared minus 7t plus 2? Well, we know in order to get 3t squared, we've got to have a 3t and a t. That's going to give us 3t squared. And then you kind of just have to think about what numbers would work in order to make your equation look like 3t squared minus 7t plus 2. And when you do that, minus 1 and minus 2, if you were to FOIL that back out or multiply it back out, you can actually get that value. Okay, so now we have our factors. And we know in order to solve for t, now we can just set our factors equal to 0. So when I set 3t minus 1 equal to 0 and t minus 2 equal to 0, I get t to be a positive 1/3 and t to be a positive 2. And so those are my t values, or the time in which the particle is at rest. If you want to figure out when it's moving left and moving right, we can just make a sign chart for that. And so I'm going to use this then to help me make a sign chart. I'm going to look at v of t, and I'm trying to figure out what's going on with the particle. So I'm going to compare that to my particle equation, which is s of t, which is the very original equation that we were given. Okay, so my critical points are t equals 1/3 and t equals 2, and I have to figure out what are the signs on either side of those so I can figure out when it's moving left and when it's moving right. So if you plug in 0 to your velocity equation, so that's this one right here, you're going to get 0 minus 0 plus 4, which is positive. Between 1/3 and 2, well, we already did that up above. Oh, that was up above. We plugged in 1 here, and we got -4, so we know that's going to be negative. If you plug in 3, I'll just tell you it's going to be positive. So now when we're dealing with particle motion, you got to relate this to the direction in which it's moving, not necessarily increase or decrease. So in this case, your velocity is positive, so you're moving to the right. When it's negative, you're moving to the left. And so you can fill out your sign chart just like that. The justification, again, is really going to be key. I already have this typed up, so I'm just going to throw it up here, and you can pause this video at this point if you want to see that. But there is your explanation right here in part B. Go ahead and pause the screen for a minute so you can get a chance to write this down. And I'm going to go back to the example here so we can keep moving for this video. Okay, so part C says find the acceleration at time t and at time t equals 1 second. We are dealing with acceleration now, which if we go back up to the PVA example, acceleration is the first derivative of velocity or the second derivative of your particle function. We already have the first derivative of velocity, so we can just take the derivative of the velocity if we want to. I'm going to just real quick write this. Your acceleration, remember, is the rate of change of the velocity. Which I already said before, your velocity is your original rate of change. So now you're taking the rate of change of your rate of change, which again seems weird, but that's what we're doing. Okay, so we just need to take the derivative of our velocity function, and our velocity function was this guy here. So we're going to take the derivative of that. And when I do that, I get my acceleration function in terms of t to be 12t minus 14. So that's in terms of t. And then if they want your acceleration function when t is 1, again, you're just going to plug in a time of 1 second, which gives you 12 times 1 minus 14. or negative 2 feet per second squared. So there is that. Part D says find the displacement of the particle between t equals 0 and t equals 3 seconds and explain the meaning of your answer. All right, so we're dealing with displacement now, which did not come up in our letters when I was giving you our example for PVA. Displacement is just really defined as the change in position. If you recall from your vector unit from pre-calc, we did talk about displacement a little bit. So this is just the change of position. And the key here is position, because we have a position function. And so the tricky part for all of these is really deciding, am I using velocity? Am I using acceleration? Am I using the position function? If you know displacement is the change in your position, that will indicate that you need to use your position function. So your displacement is just how much is it changing when you're from t equals 0 to t equals 3. So really, sorry, I'm having a hard time writing here on this thing. Your displacement is equal to your particle at 3 seconds minus your position of your particle at 0 seconds. That's really what this is. If you want to know what S of 3 is, you just have to go back into your original equation right here, and you're plugging in 3, and you're plugging in 0. So I've already done that when I worked through this example before. So I know S of 3 is 8, and S of 0 is 5. So my position at 3 seconds is 8, my position 8 meters, and my position at 0 seconds is 5 meters. So that means it moved then a total of 3 meters. So the explanation or the explain part of this, when t equals 3 seconds, the particle is 3 meters to the right of the position when t was equal to 0. So that is our explanation of what that outcome of 3 actually was. So we took t equals 3 and t equals 0. We figured out how much did it move, and our result was 3. This was 3 meters if you want to use units there. So when t equals 3 seconds, the particle is 3 meters to the right of the position when t equals 0 seconds. We're going to use that idea in part E now. It says, find the distance traveled by the particle between t equals 0 and t equals 3 seconds. So distance now, you have to take into account that sometimes your particle is moving left and sometimes it's moving right. So you can't just, the total distance is not 3 meters. That's just the displacement from where it started to where it ended, because sometimes you're going right, sometimes you're going left, and your displacement is, okay, from the original, how much did it move? If you're dealing with distance, you have to think about, okay, it moved left here, it moved right here. You have to take that into account. So we are going to compare our time to our position, which is S of t here. And we have to think about how far did it move, and that's going to give us our distance when we look at this example. And we know that t has to be greater than or equal to 0, so we're going to start with that endpoint. A critical point is at 1/3 and 2 seconds. And then our endpoint, they want to know between 0 and 3, would be here at 3. And so we have to come up with what are the values at 0, 1/3, 2, and 3. And if you recall, there is a way for you to get this table on your calculator, which I have put the equation in already. Notice that this is the position equation because we're trying to figure out how far the original particle moved. And the position equation for the particle is this equation right here. So I have this plugged in. If you want to figure out what each value is, you need to go to second and then this window button. That gives you your table set up. And if you recall from before when we did this, you want to go to the independent and you want to rather than auto, you want it to be on ask. And so then when you go to your table, which you do by second graph here, this is numbers that I had in there previously, so I suppose I can delete those out of there. We want to know when it is 0, when it's 1/3, at 2 seconds, and at 3 seconds. So that is your table of values. So you can fill that in on the table that you have here. So we're at 5, 5.6296, 1, and 8. So I'm going to come back to my screen here. We've got 5, according to our table. 5 point, I'm going to just round out to the third decimal because that's what they want us to do on the AP test. 1 and 8. Okay, so this is the position of each of the particle at each of these time increments. So from 0 to 5, you can think about it as going right 5 units. So that's that. 0 to 5. The distance is 5 units. But we need to figure out what is the distance between 0 and 3. So we want to know between 5 and 1/3 what's happening here. Okay. So in order to figure out the distance, you have to take 5 minus 5.6, or sorry, 5.630 minus 5 will give you your distance from 1/3 to 0 seconds here. And when you subtract those two numbers, you get 0.6296, etc. if you were to use your value from your calculator. I also want to know what's the distance between these two increments because those are my critical values. I know the reason we're looking at the distance between these two is because that's when it's changing direction. So you have to take that into account. So distance between 1 and 5.630 is 4.6296. Again, we're not necessarily paying attention to positives and negatives here because moving left and moving right is still moving in distance. So you want all of these numbers to be positive on the right side of the column here. And then the distance between 1 and 8 is 7. We could figure out if it was moving left or right in either of these directions if we go back to this sign chart right here. You could think about where your values are. So for 0 to 1/3, you know it's moving right. From 1/3 to 2, you know it's moving left, etc., etc. It doesn't ask us to tell you that, but I just wanted to make sure you knew kind of what was happening with that. Okay, so this is the distance traveled in each of these increments. So total distance between 0 and 3 seconds, you would need to add all of these up. So 7 plus this gives you approximately 12.2592, which a distance, if you actually use to the nearest thousandths, rounded, would be 12.259. My unit is meters. So that is the first, I guess, 1, 2, 3, 4, 5 examples from this first one. Really just paying attention to, am I using the position function, am I using the velocity function, or am I using the acceleration function? Anytime you're dealing with displacement, you're going to be using your position function. Distance traveled is, again, your original function. Anytime you're dealing with your rates, you're going to be dealing with acceleration or velocity. Okay, I'm going to stop the video there, and then I'm going to finish the examples on the next page in the following video.